Today we are going to learn about mastering ARIMA for time series forecasting. We will delve into the ARIMA model structure, understand its components, and learn how to apply it to predict future trends accurately. By the end, you'll be skilled at implementing ARIMA models to forecast effectively from your data. Welcome to our session on mastering ARIMA for time series forecasting. ARIMA stands for Autoregressive Integrated Moving Average, a popular statistical model used for understanding and predicting future points in a time series. It combines three components: autoregressive, R, integrated, I, and moving average, MA. This model is crucial for professionals dealing with data in finance, sales, or operations, allowing them to predict trends and make informed decisions. This video will guide you through understanding ARIMA's components, fitting the model, and using it to make precise forecasts. Let's dive in.
ARIMA is composed of three primary components: the autoregressive, R, part, the integrated, I, part, and the moving average, MA, part. The R component involves regressing the variable on its own lag values. The I component refers to differencing the data to make it stationary, a critical step to eliminate trends and seasonality. The MA component models the error of the variable as a linear combination of error terms from previous time periods. Mathematically, ARIMA can be represented as ARIMA P, D, Q, where P, D, and Q are integers that refer to the order of the R, I, and MA components, respectively. For example, an ARIMA 1,1,1 would include one R term, one degree of differencing, and one MA term. Understanding these components and how they interact is essential for effective time series forecasting.
Stationarity is a core concept in time series analysis. A stationary time series has statistical properties like mean and variance that are constant over time, which is crucial for the ARIMA model to perform well. Differencing is a technique to transform a non-stationary series into a stationary one by subtracting the previous observation from the current observation. This process can be repeated, termed as the degree of differencing, until stationarity is achieved. To identify non-stationary data, observe trends or seasonality in the time series plot. Once identified, apply differencing and visualize the results to ensure the series becomes stationary. This step is vital to fit an ARIMA model accurately.
To identify the P, D, Q parameters in ARIMA, we use Autocorrelation Function, ACF, and Partial Autocorrelation Function, PACF, plots.
ACF measures the correlation between the series and its lags, helping us understand the MA part. PACF measures the correlation of the series with its lags after removing the effects of earlier lags, which helps in determining the R part. By plotting ACF and PACF, we can visually inspect where the correlations diminish, indicating the potential values for P and Q. For example, if the ACF plot cuts off after lag 2, it's a sign that Q might be 2. Similarly, if the PACF cuts off after lag 1, P might be 1. These plots are essential tools for accurately estimating the parameters necessary for building an effective ARIMA model. Once you have identified the appropriate parameters using ACF and PACF, the next step is fitting the ARIMA model to your data. Start by preparing your data, ensuring it's clean and appropriately differenced to achieve stationarity. Use statistical software like Python Stats Models library to fit the ARIMA model.
Input your data in the determined P, D, Q parameters.
The software will output the fitted model along with initial results such as coefficients and standard errors. Analyze these results to ensure the model is capturing the underlying patterns in your data. If necessary, adjust the parameters and refit the model to improve accuracy. This iterative process helps in fine-tuning the model to make precise forecasts. Residual diagnostics play a crucial role in evaluating the accuracy of an ARIMA model. Residuals are the differences between observed and predicted values. Analyzing them helps ensure the model's assumptions are not violated and that it's well fitted to the data. Begin by checking residuals for patterns. Ideally, they should appear as white noise, indicating no patterns are left unmodeled. Use statistical tests such as the Young box test to confirm the randomness of residuals. Visualize the residuals using histogram plots and QQ plots to assess normality. If residuals display patterns or fail normality tests, consider revisiting your model's parameters or exploring transformations. A robust model will have residuals that demonstrate no significant autocorrelations, ensuring reliable forecasts.
While ARIMA is effective for non-seasonal data, many time series exhibit seasonal patterns that ARIMA alone cannot capture. Enter SARIMA Seasonal ARIMA. SARIMA extends the ARIMA model by adding seasonal components to account for repetitive patterns over fixed periods. It includes additional parameters, P, D, Q, which represent the seasonal parts of R, I, and MA, respectively. Start by identifying seasonal patterns in your data, typically through visual inspection of the time series plot or by applying seasonal decomposition. Once identified, determine the seasonal orders for SARIMA. For instance, a SARIMA 1,1,1,1,1,12 model applies a monthly seasonal pattern with one seasonal R, one seasonal differencing, and one seasonal MA component. Implementing SARIMA involves similar steps to ARIMA, with the added complexity of seasonal parameter estimation. Mastering ARIMA allows for comprehensive modeling of time series data that exhibit both seasonal and non-seasonal patterns.
Implementing ARIMA models in Python is straightforward, thanks to libraries like stats models and pandas. Begin by importing these libraries and loading your time series data into a pandas data frame. Conduct exploratory data analysis to understand the data structure. Use the stats models library to perform differencing and plot ACF/PACF to identify parameters.
Once you have P, D, Q values, use stats models ARIMA class to build and fit the model.
Interpret the output, focusing on coefficients and diagnostics to ensure the model is well fitted. Visualize the forecast results using matplotlib to compare predicted values against actual ones. Be cautious of common Python pitfalls such as data type mismatches or incorrect parameter specification. With practice, Python becomes a powerful tool for implementing ARIMA models, enabling you to leverage your data for accurate forecasting. Despite its power, ARIMA modeling comes with challenges that can lead to inaccurate forecasts if not addressed. Overfitting is a common issue, occurring when the model is too complex and fits the noise rather than the underlying pattern. Simplify the model if you notice overfitting. Non-stationary residuals indicate the model hasn't fully captured the data stationarity, requiring further differencing or parameter adjustment. Parameter estimation can be tricky. Ensure you're using the correct ACF/PACF plots and watch for signs of model misspecification. Seasonal data presents unique challenges. Ensure ARIMA parameters are accurately estimated and seasonal patterns are appropriately modeled. Adhering to best practices, such as cross-validation and continuously refining your model, helps mitigate these pitfalls, ensuring reliable ARIMA forecasts.
In conclusion, mastering ARIMA for time series forecasting equips you with a powerful tool to predict future trends accurately. We've explored the components of ARIMA, the significance of achieving stationarity, and the method for identifying parameters using ACF and PACF. We also discuss the importance of evaluating model accuracy through residual diagnostics and the complexities of handling seasonal data with ARIMA. Practical implementation using Python was covered, highlighting the benefits and possible pitfalls. Continue practicing these skills, applying them to diverse datasets to refine your expertise. With dedication, ARIMA can become an invaluable part of your analytical toolkit.